Hi, my name is Faisal Chaudhry. Today I will discuss the concepts and principles behind the motion of a falling object as it falls straight down from a state of rest. The object I will be using is a beach ball, and I will drop it from my hands at a height of 1.5 meters. This is the video I recorded of the beach ball falling. Before I show you my data and results, I wanted to discuss the fundamental principles behind the motion of a falling object. Newton's second law states that the acceleration of an object is proportional to the magnitude of the object's net force. Since the ball is falling straight down, instead of moving at a constant speed in the x direction, the initial velocity will not be the same as the final velocity. Therefore, in the velocity update formula, there has to be some net force acting on the beach ball as it falls for the formula to agree. That net force is the force of gravity, or mass times g, of the ball as it falls towards the Earth, in the negative y direction. In an ideal world, the force of gravity would be the net force acting on the ball since there are no other forces causing the ball to fall. However, there is a resisting drag force in the opposite direction of the ball's motion, which is up, that is changing the net force of the ball as well. The constants in the drag formula are the density of air, the area of reference for the ball, which is pi r squared, and the drag coefficient. As the velocity squared of the ball grows, then the force of drag will grow as well. Now on to the data. I uploaded the video of the ball falling into Tracker to track its y position over time. The ball's mass is about 0.11 kilograms, and its radius is about 0.22 meters. I used these initial quantities to calibrate the motion, and I tracked the average position in each frame of the ball falling. It produced this y position graph that indicates a changing velocity per time in the negative y direction. I updated my starter GlowScript code to include the initial measurements from Tracker that I found, and I updated the while time loop to reflect the duration of the ball falling, as well as the position and velocity update formulas and the update of the net force. For the gravity-only computational model, I included only the weight measurement of the ball in the negative j hat direction, pointing down as the net force. This produced a model where the ball gradually increases speed as it fell, resulting in a similar decreasing position versus time graph to Tracker. For the gravity and drag computational model, I included both the weight measurement and the force of drag of the ball in the net force update, along with the same initial conditions as the first model. The force of drag is in the positive j hat direction, indicating drag opposing the direction of motion. The coefficient of drag was estimated using the final position of the ball compared to Tracker, and it resulted in a similar decreasing position versus time graph as well. Now on to the results. The observed Tracker graph looks different from the predicted computer model graphs that were generated in GlowScript because the time step of Tracker was much larger, giving less precise data points. The time step in GlowScript was much smaller, which resulted in a more precise graph, differing only by the position the ball landed on. Between the gravity-only and gravity-drag graphs, there is a slight difference that shows how drag can move the ball from an ideal position when it falls, but the result is not noticeably significant. Now let's talk about terminal velocity. Terminal velocity is when the gravitational weight of the object falling equals the amount of drag resistance in the opposite direction, creating a constant velocity of the falling object. Therefore, over time, if there are no other forces acting on the object besides gravity and drag, and they are both equal, then the ball will fall at a rate of 9.8 meters per second squared towards the Earth. Both graphs are similar in their change in velocity graphs, but gravity and drag graph will predict terminal velocity eventually because it takes into account both forces, whereas the other graph does not. And it will slowly trail into a flat line to show that the ball will reach terminal velocity eventually if more time is allowed. If the ball is thrown down with an initial force, the ball will have an initial velocity in the negative y direction, meaning that the ball will not fall from a state of rest. With an initial force of the throw, the ball will accelerate towards the Earth at a faster rate than usual, meaning that it will take longer for the ball to reach terminal velocity. The ball will fall faster and take longer for it to reach a constant velocity after a long time. In this case, the terminal velocity will be different because the ball releasing from a state of rest will eventually reach terminal velocity quicker than when it is thrown down initially. And so, if there is an initial force of the throw, the ball will travel faster and it will take longer for the graph to flatline at a constant velocity change of 9.8 meters per second. In conclusion, the falling beach ball has a non-zero net force acting on it because the forces of gravity and drag are causing it to accelerate towards Earth at a non-constant rate. The velocity is changing over time, reaching terminal or constant velocity change in velocity once the ball falls for a long time from a much higher distance. Thanks.